Hi everyone. Today I'm going to be doing a video about triple integrals in rectangular coordinates. And what that means is that when we go to find the volume of some surfaces, it's going to look like a triple integral with a 1 here. And then the rectangular part of that means that we're looking at things like dx, dy, and dz. So it's going to be some combination of them. And a big part of this section is going to be kind of choosing the order of which integral we want to do first. So whatever this interior integral is, that's the one that we want to do first. And we'll kind of look at what these volumes look like if you try to choose them, because that's going to determine not only what goes here, but also here as well. So kind of making the right decision out of these three in the beginning is going to save you a lot of trouble in the future. So there's a few things that go into making that decision. One of which is that just like in double integrals, we want to have our constants on this outer integral, and then we want to have a function in this integral. This function can only be of one variable. Right, so maybe this is y equals f of x, or y equals some function of x. And then this last piece here, we can actually put surfaces on here. So I'll show you what this looks like in a drawing, and then I'll kind of put the order that I want on here. So if I draw two surfaces, so maybe I've got a wavy surface up here, and I'll call that one F, and let's say I've got a spiky surface down here. We'll call that one G. If I'm interested in finding the volume, right, in between these two surfaces, the way that I'm going to want to set this up is that is like follows. So these are both functions, presumably of x and y. That is to say, like z equals some function of x and y, and for this one, g of x and y is also some function of z. The reason I know that is because along the z-axis, they pass this vertical line test, right? Like as I kind of pass through them, I'm only hitting the surface once, but if I try to go either this direction or along the x-axis, I'm going to run into some double hits. Right? I'll touch the surface twice. So you'll see this in the equations that we look at, but if we've got two surfaces where z equals those surface, then our volume is going to be, right, some double integral, and then in this integral here, in this interior one, I'm going to put my f on top, right, because that's the top surface. That's going to go there, and my bottom surface is going to go here. And that first variable is going to be dz, because these are both z values, right? Z equals blah, 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 z equals blah, blah, blah. So I'll put dz there. And as far as the next two integrals go, kind of a new topic that I want to introduce is this idea of a shadow or projection. So the way that I think of this is if you've got a flashlight, right, and you shine that flashlight down the z direction, you kind of want to think about the shadow that this volume is going to create. And so that shadow, if I can kind of make a rough sketch of it, that shadow is going to look something like this. So that shadow, that rectangle in this case, we'll say this shadow determines the bounds of the other two integrals. Right, so it's going to be these two integrals here. So whatever this shape is, we've got lots of practice, right? Taking solids like this and turning them into double integrals, or taking double integrals and turning them into this shape, right? So that's all we're going to be doing. So I'm just going to put them in an arbitrary order, dx, dy for the rest of them. Maybe x is in between 0 and 2, and y is in between 0 and 3. Or sorry, y is in between 0 and 3. Right, something like that. Just to see some contrast here before we get into an example, we can also look at a situation where, let's say I've got my wavy surface out here. And I've got some, I'll call this one H. And let's say that I've got a fiery, spiky surface out here. We'll call this J. The most likely scenario for this one, when we're trying to find this volume in between these two surfaces, is that J is going to be a function of x and z. That's going to be equal to y. So I'm using these kind of abstract shapes to demonstrate a point about kind of the nature of surfaces, right? So surfaces are just functions of two variables. In this case, y is equal to x and z. Later on, when we actually look at the example, we'll see that these functions will be given to you, right? You'll see, for example, that maybe y is equal to x squared plus z squared, or something like that. That will just be given to you, and you can intuitively say, well, this is a function of y. But in any event, we'll see that in the example. For now, we can look at the volume of this piece here, and we'll put, so here's the question, which one goes on top, right? Got our x, got our y, got our z, and what we did without saying it really here was when we went from kind of this z equals infinity spot when we're trying to figure out which one goes on top and which one goes on bottom. We went from z equals infinity, and here we intersected the f first, and then we intersected the g first. So I know it's really obvious here, right? F is on top, g is on the bottom. But we're doing that same thing here. We just kind of want to see which one has the most positive y value. So we're going to kind of drop a line here. Looks like we intersect the h first, and then we intersect j second. So in this case, the one that's going to be on top is h. So we'll put h up in there, and we'll put j down here. And then the order for this one is going to look like dy. And then for these two integrals, we want to think about the shadow that's cast. So this time, when we talk about that shadow, our flashlight's going to be pointing this way. So if we picture kind of the shadow left behind by this one, I'm just going to draw it out here so we can see it. I think that shadow looks like a rectangle, something like this again, right? In our example that we do, we'll look at more interesting shadows, but for now, we'll just kind of say there's a connection, right, between this shadow and these two integrals. So I'm just going to put them dx, dz, right, in just an arbitrary order, right? X is in between 0 and 3, z is in between 0 and 2, something like that. Okay. So what I'm going to do for this example is I'm going to be looking at the same volume, the same solid, and I'm just going to do it in all the different orders. All right, there's actually 6 different orders: dz, dx, dy, dx. I won't write them all out, but there's 6 of them. Right. So I'm going to at least look at 3 ways to do it where I have the I change that kind of first integral that I do. So we'll see one where we do x first, y first, and z first. And the solid that we're going to be looking at is as follows. So here's the problem. Find the volume of the solid bounded by so 2 surfaces. One is x equals 4y squared plus 4z squared, and x equals 4. Already I can look at this problem before I even sketch it and say, hey, look, x is a function of y and z, and this is also a function of y and z, so maybe dx is going to go first. Maybe that's a good idea. That turns out to be true, but I want to show you what they look like in the different orders. So let's start off with a sketch of what this thing even looks like. So I'll give myself three-dimensional plane. And I kind of know what this one's going to look like, so I'm going to give myself a nice long x-axis. So if I'm sketching this one, right, we know what x equals 4 looks like. That's just a plane, right, at 1, 2, 3, 4. That's the plane of all the values where x is equal to 4. So we'll sketch that in just a second. But if we want to sketch this one, we can kind of make our coordinate plane traces. So when x equals 0, that's going to look like 0 equals 4y squared plus 4z squared. And our quadric surface, right, ideas didn't go anywhere. So this is a circle with a radius 0, or the only values that work here are y equals 0, z equals 0. So that's a point. If we set y equal to 0, then we get that x is equal to 4z squared. So if x is equal to 4z squared, that's going to be a parabola. This is a point. And the parabola is going up the positive x direction. So maybe it looks something like that. And we get something similar when we set z equal to 0. So my sort of parabola in that direction. So you can kind of start to see what this shape is, but we want to know what happens when, right, this is our plane x equals 4. We kind of want to know what happens when we intersect that plane, right, at x equals 4. So maybe we'll set x equal to 4 and see what's happening over here. So that would look like 4 is equal to 4y squared plus 4z squared. And we see that we get a circle with a radius 1. So at x equals 4, I'm getting a circle with a radius 1. That's kind of what the intersection of this surface and this plane looks like. So overall, this is kind of the shape of our shape, right? All right, so it looks like the bullet or something like that, but it stops right at x equals 4. So maybe we can label that plane there. So like I was saying before, it seems like x would be a good interior integral or first integral to do. So when I set this up, looks like this, and I'm going to start with dx and do that version. So the question is, kind of which surface do I hit first? And if I'm going through this from the positive x infinity, the first thing I hit is this plane, x equals 4. And then I hit this surface. So if I kind of take any of these lines, I hit the plane, and then I hit the surface as I go through there. So my top surface is going to be 4. My bottom surface is going to be this 4y squared plus 4z squared. So I'm actually going to draw that in the same. All right, so now you can see this is a function of y and z, and it's dx. This one's a function of y and z. It could involve y and z if we wanted it to, but right now it's just got the 4. So that's all we needed, right? Top surface, bottom surface, and this is the volume in between them. Now, what I said last time was that we want to kind of picture a flashlight creating a shadow if we want to figure out what these two look like. So if I shine this flashlight here, and by the way, this flashlight is not something you'll see in the book. Your book gets into talking about these as being type 1 and type 2 and so on, and I think that's a perfectly valid way to think about these, but you won't have to ever think about what type something is if you just kind of follow this shadow principle. So if I'm shining the shadow down the x-axis, it doesn't make sense to set z equal to 0. We kind of want to see what the biggest shape we can make, like what's kind of the largest shadow we have here. And I think the largest shadow is going to be kind of like right at this end of it, right? So the shape of that largest shadow is going to look something like this, right? So I think for that largest shadow, For the shadow, what we're looking at is this shape, right, in the YZ plane. Just looking at that circle. And the radius of that circle is the same as this cap here, which is 1. So there's our shadow. And if we wanted to find that with a double integral, that's just exactly the way we would do it before. So we looked at kind of what circles look like when we express them in these rectangular coordinates. This would be a good time for polar coordinates, right? It's not crazy to want to do polar coordinates here, but we'll get into that when we talk about cylindrical coordinates. But for now, I kind of want to talk about this as being like z equals this top surface here, z equals this bottom surface here. So I'm going to say dz, and then z is in between square root of 1 minus y squared and negative square root 1 minus y squared. So just the top and the bottom half of the circle. And then dy is just going to be in between negative 1 and 1. If we wanted to figure out the actual volume of this, all we would need to do is just solve this triple integral. So we would do this integral with respect to x, then integrate with respect to z, then integrate with respect to y. Because that's going to be a long process, doing double integrals was already long enough. Most of what I'm going to have you do is just set these up, right? I will be impressed if you set them up, and then I'll trust that you can do, if you can do a double integral, then you can do a triple integral as well. So just setting it up, that's what this is going to look like. Surfaces, functions, constants. So that's what it looks like in one order. I'm going to draw that same object in just a and then we'll integrate it in a different order. So that same object, you get the idea. All right, looks something like that. So this time, ask what about dz first? So this one's going to be a little bit trickier, but if I look at my triple integral, what I'm going to need is two surfaces. So I put dz here. The idea with this one is I'm going to start from positive z, and I'm just going to kind of see what surfaces I hit. So it looks like I punctured this surface right once, and then out the other end. And if I drop a few more just to kind of get the idea, maybe one over here, puncture it, puncture it. So I've actually got two surfaces here. I'll try to highlight them as best I can, but really I have kind of the top of this bullet shape. And then my other surface is going to be the bottom. Okay. So when I go through here, I'm hitting the top surface and then I come out the bottom. So in terms of what that looks like, I'm really just going through this same surface, right? I'm going through my x equals 4y squared plus 4z squared. And so I'll start off with that x equals 4y squared plus 4z squared. And like I said, I'm really just going through that same surface, x equals 4. Unless I'm right on the edge here, I really don't ever travel through that surface at all. So what I need to do, if I'm going to put dz first, is I want to have two functions of x and y. So putting it in terms of z, I can get something like 4z squared is equal to x minus 4y squared. And then z squared is equal to x over 4 minus y squared. And then when I solve for z, I remember squared here, I need a plus or minus. I end up with this, and it turns out that this plus or minus here just represents these two surfaces, right? These are all the spots where z is positive, and these are all the spots where z is negative. So that's going to be my first integral, right? My function on top, f, is the positive one, and then g is my negative one, if you want to think of it that way. So this is going to be positive x over 4 minus y squared, and this is going to be negative root x over 4 minus y squared. Now, in terms of the other two integrals, I need my flashlight, and this time the flashlight is going in this direction, right, shining downwards. So if you think about what that shape looks like, the largest shadow that it can make is really kind of happening right at this seam here. All right, it's not happening at z equals 1 or anything like that. So the z value where this shadow is occurring, if I can kind of draw it down here, looks something like this. Kind of that surfboard shape. So, so that shape in particular happens to line up with what's happening right at the seam here. We can say our shadow looks like the shape that occurs at z equals 0. And that'll often be the case where if we want to figure out what the shadow looks like, we just need to set that interior integral value to a particular value. Before I get into the actual computation of that, I just want to show you we really did the same thing here, right? The shadow happened when x was our first integral. This shadow happened when x was equal to 4. So if we wanted to set x equal to 4, we could get that same shadow. But in this case, it's when z is equal to 0. So if we set z equal to 0, just a reminder from above, we get that x is equal to 4y squared. And we of course know that we're going to get this kind of shape from it, parabola. Kind of in this direction. And I'm stopping here because we also know that here's the plane x equals 4. All right, that's kind of our boundary there. So here's what it looks like in the xy plane. And if we project that over, that's what it looks like in 3D space. So anyway, here's our shape. And we can split this up into a top curve and a bottom curve. We could also even decide to split this up into this curve and this curve here. But I think that I'm going to do it this way. I'm going to say this is a top curve and a bottom curve here. And if I want to figure out what those curves are, just a little bit of algebra will do that. So we'll get taking this a little bit further, x divided by 4 is equal to y squared. So that means that y is equal to plus or minus 1/2 times square root of y squared. No, what am I saying? Square root of x. Right? Or root x over 4. Maybe I'll keep it there. There we go. So y is plus or minus root x over 4. So going back up to our integral, we can say dy, y is in between positive root x over 4 and negative root x over 4. And then finally dx, those are our constants. This one's nice and easy. X is in between 0 and 4. Just to look at that alternative way to think about this. Again, we could think about this as being a function that looks like this, and function that looks like this, and say this is our quote-unquote top curve, right? As we travel along the x direction, we hit this curve, and then this is our bottom curve. Let's see, that was y. So we could say, starting with that same piece there, x is equal to 4y squared, and x is equal to 4. This is our top curve and our bottom curve, so we could say that, let's see, this was square root of x over 4 minus y squared, root x over 4 minus y squared. That was a function of z. Dx, in this case, we could say that x is in between, remember 4 is our top function, right? More positive x valued one. And then the bottom one is 4y squared. Really all that we need to do differently in this one, right? It seems like we came up with something easier here. But unfortunately, for dy, we don't really know Well, I think we figured that out, right? We did. That happens at 1. I guess what I wanted to get across with that is we would have to find these intersection points. But again, this is the circle, right, at the end of the the flat end of our shape. So y is just going to be between -1 and 1 because that circle had a radius of 1. I'll quickly do the next one and then kind of talk about strategy with picking the order of these things. But hopefully you can at least see in this one that it's a little bit easier in that first direction that we did where x was in between this solid and this solid over here. But definitely doable in all 3 directions. There we go. So this time we'll do, what if we did, let's see, the only thing left is dy first. So very similar to the last one, right? Except we're hitting a right and left surface here. Right, so the split's going to occur down the middle here. Okay. So those are 2 surfaces, and if I drop a line through here from y equals positive infinity, this is the top one, this is the bottom one. So I think I'll save us all the trouble of doing all that computation because it's very similar to what we saw last time. But I'll just point out that our shadow shape is just going to look like this if we shine a flashlight on it, and that's the case where y is equal to 0. All right, that plane y is equal to 0. Now I'm drawing too much on it. There we go. When y is equal to 0, that's when we have that split or that largest shadow in between them. But just so you can see what this looks like, dy is going to be, let's see, the integral x over 4 minus z squared negative and positive versions. Next we can do, we're talking about this shadow here, so we can talk about, let's do x next. So x in this is going to be same thing, 4 on top here. And then this piece of it, right, the parabola, that's going to be the bottom piece, and that is going to be 4z squared. And then our dz, again, that circle is a radius of 1, so that's going to be between -1 and 1. So those are the 3 ways to look at this shape. And it was doable in all 3 orders. In fact, any of the 6 ways that we can combine dx, dy, and dz worked. But I'll say this, some shapes are much more difficult to integrate in certain orders. So here's a shape that I'm going to go over. So I'm going to attempt to draw this shape kind of doing a front, side, and then top view, just so you can get a feel for what that looks like. So here's what it looks like from the side, or what I guess I'll call this the front. So here's what it looks like from the front. And then if I turn it 90 degrees, right? So if I look at the side view of it, it looks like this. And then from the top, it looks like this. So kind of that spot right there marks the beginning of this. Oh, I messed that up bad. All right. So if you can picture it, right, this is if I rotate it right this way, and then looking at it head on, that's this view here, but it's like a lipstick type shape, right? And I'll try to graph this in 3D. Pick a nice lipsticky color. So I'm going to draw it in this direction. Let's say it starts off like a cylinder in this direction, and then it that's not half bad. Maybe a little bit difficult to see, but all right, so that's the shape. All right, it's got this kind of you know, planed end on the side of it, and then a circle back here. The point I want to get across with this one is that if I tried to, let's say, do dy first, I could definitely do it, right? I can hit this surface, and then I hit this back surface, and there's no trouble with kind of running into this plane, right? It's nice and square with it. But the issue is the shadow that I'm going to leave behind looks like this. And that shadow is going to be really hard to define, certainly in terms of like a top and a bottom, just because this top part here, right, in terms of Z, like this is the top, but this is also the top here. And we don't want to have to split it up in that way, right? It's sort of like that Calculus 1 problem from your homework, right, where you have something like this. You definitely want to do it in this order, where this is the top, and this is the bottom, because trying to do it the other way, where this is the top and this is the bottom, you run into all kinds of problems, right? Because, well, the bottom is this, or is it this one? And you kind of have to split it up in between those two. So it's just bad news. You don't want to have to do that. So dy first, we'll say this makes an awkward shadow. So that's kind of one of the things that you want to consider. I think the best one, dz first is also going to make this as a shadow. Actually, this is really what it looks like. But I'll do this in a different color. If I do, I'll say maybe DZ2, right? Because, right, the shadow that gets left behind there looks kind of like this. That's going to be difficult to find. But the DX shadow, so do that one last. The DX, that's going to give a nice shadow. So what that shadow is going to look like is, if I shine my flashlight on this shape, the largest shadow just happens to be where this circle is. So that shadow is just going to look like this. And if we can figure out what this surface and this surface are, right, in terms of x, then that shadow is going to be the nicest one. This is kind of an example of a shape where the order is going to matter in terms of setting up that triple integral. And it's sort of hard to quantify, but this is just something I think about a lot when I'm choosing this order for myself. You sort of want your most complicated cuts to be here, and you want your simplest cuts to be here. So the way that I think about that is, let's say you've got some kind of block of cheese example. Right, where this is your shape, and let's say that it gets like really complicated. All right, you've kind of got the most complicated cut right here. So this is your x-axis, this is your y-axis, and this is your z-axis, right? So what I would say here is I'm looking at this thing, and the simplest cut that I can make is that x rather, x is in between those two things, right? I can make that cut out of all of 3D space, and I can say that, right, x is in between, 0 and 4, or whatever that is. And the next easiest cut to make is to say that z, well, that's another easy cut too. That's another really easy cut to make, is that z is in between, these two spots here, right? So it's in between 0 and maybe this is -2 down here. But if you ever have something, right, that's complicated, you want to save that for this interior-most integral. So the y is in between right, this shape. So we'll call this wavy. Right, that's going to be in between this wavy surface and looks like 0 here. Right, but kind of the more complicated something is, the closer you want it to this inside integral, because I call these surfaces, but what they really are, if we look back to kind of the original setup where I was talking about that, they're really just functions of two variables. So I saw a lot of work on what the order could be. That was on the last page. So I said constants here, functions of just one variable, and these surfaces here are really functions of two variables. So that's going to be it for now. I will, in class, I know there's a WebAssign question that goes over kind of sketching one of these 3D surfaces, and it's not as straightforward as the one we went over. So I'll look into that, and we'll see that on Wednesday. All right, see you then.